Hi again, this is second video of this chapter and we will learn and discuss about the kinematics in one dimensions. So, the first topic is about the difference between distance and displacement. I believe you heard this before, whether in your secondary school or last week lecture. So, what is distance? So distance is a scalar quantities that refer to this statement: how much ground an object has covered during its motions. You all know that scalar quantity is a quantity only with the magnitude, right? While vector quantity is a quantity with both magnitude and directions. Now, as an example, in this figure over here, a person was travel from this point to this point. So the distance this person travel is what we call as a distance. It has magnitude, it has only magnitude. Meanwhile, displacement is a vector quantity that refers to this statement, which is how far out of a place an object is. Displacement is the object's overall change in positions. So back to this example, even this person travel far to reach the final destinations, but then it should be shortened. So this is what we call as displacement. Now displacement, or we symbolize it as delta x of an object, is defined as its change in positions. Now, when we are looking at the upper figure here, it is described here how the car moves to the right positions from positions A to positions B. Now this movement or motions of car will cause us what we call as a change of distance, delta x. Delta x is the difference between the final positions, this is F, to the initial positions, this is I. So delta x is equal to xf minus with xi, and the SI unit is meter. For this upper figure, you're supposed to get a positive change of delta x. As you can see over here, the final positions is bigger than the initial positions. On the other hand, in this lower picture over here, this similar car is start moving to the left from point C to point F, which is the final positions of the car. Now in this case, you will get a negative value of delta x due to the value of finals is much smaller than the value of initial. So the value of delta x, which is the change in distance, will be in negative or positive or zero. Now this slide shows the graph of positions with time of the car. If we observe from its initials over here, A, which is to the point final, which is B, you can see that this particle or this car is moving increasingly with time. Now if you calculate this gradient over here, you will get a positive value of gradient. But from point B to point F, which the car is moving slowly with the increasing of time, you will get a negative value of the gradient. So the difference of value that I have gathered from this slide and this slide is, in this slide we will only talk about the magnitude of delta x for the car, which what we call as a distance. However, in this slide we will talk about the magnitude and the directions of the car, which represent the displacement. Now, I hope by now you will be able to differentiate between distance and displacement. Distance versus displacement is not the only value quantity that you need to know to differentiate. Speed and velocity is another quantity that you should know the difference between each other. So speed, similar with distance, is a scalar quantity. It is a magnitude of velocity. On the other hand, velocity is a vector quantity that refers to this statement: the rate at which an object changes its positions. In our everyday language, you can hear people use the word speed and velocity interchangeably. But in physics, speed is a scalar quantity having only magnitude, while for velocity, which is a vector quantity having both magnitude and directions. So why is velocity being a vector? Imagine if you want to get a town 70 kilometers away in an hour time. It's not enough to drive at a speed of 70 kilometers per hour. Pretty obvious, you will travel in the correct directions, which you must travel in the correct directions as well. Well, pretty obvious, right? But you can see that velocity gives more information than speed. Now, average speed can be found by dividing between the path length, which is symbolized as the d, over elapsed time, which is our t. And the SI unit for average speed is meter per second. Let's see an example here. The straight line distance from Kota Kinabalu to Tawau is about 550 kilometers. If someone drive a car that distance in 8 hours, the car's average speed is supposed to be 550 divided by 8, which also equal to 68.75 km per hour. It doesn't matter if the driver's speed changes during the trip. The driver could run into traffic and have to slow down or stop along the way, or drive faster for part of the trip. The average speed is still the same. But let's say the drivers make a side trip to Kalabakan, which might added 50 kilometers to the path length. So now the average speed, so now the distance trip is equal to 600 kilometers. Now the average speed now is 600 divided by 8 hours, which is equal to 75 kilometers per hour. Distance is the length of a straight line joining 2 points, and path length is the length of the actual path transverse between 2 points. The average speed of an object over a given time interval is the length of the path it's traveled divided by the total elapsed time. We can also write this equation symbolically, just like this one, where V representative the average speed. Delta x or delta d represent the path length. T is the elapsed time during the motions. Right. Average velocity is a vector quantity which has a magnitude and a directions. Let's look at our figure again. Let the car positions be xi, which is initial positions, at some time ti. Let the car positions at later time tf to xf. In the time interval, delta t is equal to t final divided minus with t initials, while our displacement is delta x is equal to x final minus with the x initials. So the average velocity during a time interval at this point delta t is this one. Now average speed is always positive, but the average velocity of an object in one dimension can be either positive, negative, or zero depending on the sign of the displacement here. Now in the top figure, the average velocity of the car is positive, as I said earlier, because it starts at point A and ends at point B. A plus sign indicates motion to the right of the x-axis, while in the bottom, the average velocity of the car is negative, because it starts from the biggest number to the small number. And minus signs here indicate motions of the car to the left of the x-axis. Right. Let's see over here. A drag race view from a stationary beam. One car follows the rust color over here, the straight line path from P to Q, and a second car follows the blue curve over here. Imagine we are watching this drag race from a stationary beam. The path of a car are depicted in the figure. In one run, we can see a car follow the straight line path shown in orange from P to Q during the time interval delta t, and in the second run, a car follow from the curved path shown in the blue during the same time interval. Now the two cars have the same average velocity because they have the same displacement during the same time interval, right? Now the car taking the curve route travel a greater path length and had the higher average speed compared to the car that follow the straight line. Right, we continue. This is a graph of positions versus time. This figure shows a graph from the data in this table. Here, the position versus time is not a straight line, as you can see over here, the orange line. We can still draw a straight line between any point, and the slope of that line is the average velocity delta x over delta t. In general, the average velocity of an object during the time interval delta t is equal to the slope of straight line joining the initial and final points on position versus time here. Okay, we continue with the next topic, which is instantaneous velocity. If you are on a car trip, you might speed up or slow down because of traffic or road conditions. Average speed doesn't give us these informations. If you want to know the speed and directions you are driving at a particular instant, you want the car instantaneous velocity. Now, when you drive from one point to another, the average velocity is computed over an interval of time, just like this one. But the magnitude of instantaneous velocity can be read on your car speedometer as shown here. So this is speedometer in your car or in any mobile. The instantaneous velocity, which is V over here, this is the equations, is the limit of the average velocity as the time interval delta t become infinitesimally small. So the notations here means that the ratio delta x over delta t is repeatedly evaluated for smaller and smaller time interval. As delta t getting extremely close to zero, the ratio get closer and closer to fixed number, which is defined as instantaneous velocity. The SI unit for instantaneous velocity is similar with the velocity, which is meter per second. And instantaneous velocity can be positive, negative, or zero. Now, the data in this table shows the positions of a car at specific instance of time. We can use this data to construct the table over here. So let's do some calculations. In the interval from 1 to 3 seconds, the displacement is 52.5 meter minus with 5 meter. So our average velocity is supposed to be 23.8 milli per second over here. You can read over here the velocity is equal to 23.8 from time interval 1 second to 3 seconds. So using the final interval of only 0.01 second, we calculate the average velocity is 47 meter per second. So this is the average velocity. Since this is very short time interval, the actual instantaneous velocity is probably very close to the average velocity. Right. So there are three types of acceleration that we can use to describe the motion regarding acceleration. Increasing speed, decreasing speed, and also changing directions. This type of acceleration can be also shown in a form of graph just like this one. When a car moving to the right over here, it accelerates from a velocity vi to vf in the time interval delta t, which is ti and tf. So it is written over here. When you're driving this car, it's rare that you travel for long distance at constant velocity. The velocity of the car increases when you step harder on the gas pedal and decreases when you apply the brakes, of course. So the velocity also changes when you round a curve, altering your directions of motion. So this changing of an object velocity with time is what we call as a accelerations. So in this figure, the car moves along a straight highway. At time ti, it has velocity of vi, and at time tf, it has velocity of vf. So the average velocity, the average acceleration during this time interval is the change of velocity divided by change of time. And the SI unit for accelerations is meter per second square. As you can imagine, the value of average acceleration is often differentiated for interval time, for different interval time. So it is useful to define the instantaneous acceleration, which is also similar to the definitions of instantaneous velocity that we just talked about. So the instantaneous accelerations, which is we symbolize as A, is the limit of the average accelerations as delta t approaches 0. Again, the notations mean that the ratio delta v over delta t is evaluated for smaller and smaller value of delta t. And the closer delta t gets to 0, the closer this ratio gets to a fixed number, which is what we call as instantaneous acceleration. Right. In our study of mechanics, we will often be dealing with the situations of constant accelerations. This type of motion is very important because it applies to many situations, including an object in free fall near Earth's surface when air resistance can be neglected. This top figure over here shows motion with constant accelerations. So when an object moves with constant accelerations, the instantaneous acceleration at any point in a time interval is equal to the value of average accelerations over the entire time interval. That means the velocity increases or decreases at the same rate throughout the motion. And a plot of v versus t shown here at the bottom give a straight line over here with either positive, 0 or negative slope. Since the average accelerations equals the instantaneous acceleration when a is constant, we can eliminate the bar used to denote average value from our defining equations over here. So we have these equations. Now let's choose ti over here is equal to 0 and tf is to be arbitrary time, which is t, and let vi is equal to v naught, which is initial velocity, and at t is equal to 0, and vf is equal to v, which is our final velocity. So our equations will become like this. And by rearranging these equations over here, we will get the first equations of kinematic, which is v, final velocity, is equal to initial velocity plus with the accelerations times with the time. So this equation states that the acceleration steadily change the initial velocity by an amount of at. Now, since the velocity is increasing or decreasing uniformly with time, We can express the average velocity in any time interval as the arithmetic average of the initial velocity and the final velocity divided by 2. Keep in mind that these expressions is only valid for constant accelerations only, in which case the velocity increasing uniformly. Now let's combine this result over here with our definitions of average velocity. So it will become just like this one. And we set our Ti is equal to 0, Tf is equal to f, and this one is a change of distance. So our new equations will be this one. And by rearranging this one, our result is an expressions of delta x, which can be rearranged to give us the equations number 2 for kinematics. Right. We can make a substitutions in our result for delta x using our equation for v. We get our third kinematic equations, which is this one. So as you can see over here, delta x is the change of distance. This is initial velocity, this is initial velocity, this is our constant acceleration, and this is t. So it will become, this is eventually will become just like these equations. So this is our third kinematic equations. Now finally, we can obtain an expression that doesn't contain time. So by substituting our equations number 1 into our equations number 2 and solving our velocity equations for t and simplifying all of these, we will get our last but not least kinematic equations, which, as I said earlier, this is only applied for a constant acceleration where the v is increasingly uniform or decreasingly uniform. Now this table over here show our 3 equations in summary. Remember, these are for constant accelerations only. Right, we come to our last subtopic for this second video. When air resistance is negligible, all objects drop under the influence of gravity near Earth's surface fall down toward Earth with the same constant accelerations. Now, the accelerations of this gravity for object in free fall at the Earth's surface is negative 9.81 milli per second square, which is our g. Galileo found that all things fall at the same rate. That's why this one is out. So the ideal case where we can ignore air resistance is what we call as a free fall. Object thrown upward or downward and those released from rest are all considered free falling. So as you can see over here, the rate of falling increases by 9.81 meter per second every second. And I want to emphasize that you need to use the accurate value of g, which is equal to 9.81 meter per second square. Don't use 10 or 9.80. Please use the accurate one. So if we neglect air resistance and assume that the free fall acceleration doesn't vary with altitude of a short vertical distance, then the motion of a free falling object is actually the same as motion in one dimension under constant accelerations. This means that we can use our kinematic equations. So as you can see over here, this 3 is the kinematic equation that we just come up just now, and we can use for free falling object. So it is conventional to define up as the positive y direction and positive y as the positions variable, which that means A is equal to negative g, which is go down. So our equations, our 3 kinematics equation will become like this. So this is supposed to be positive A, this is supposed to be half A, this is supposed to be positive 2A. But then when the accelerations is changed into negative g, then my new equations for free fall is equal to this one, and this one. Now that's all for kinematics in 1 dimension. Keep watching my last video for kinematics in 2 dimensions.